algebros. Now we are going to be talking about the characteristics of cubic functions. So cubic functions are a little crazy. They have two curves in them instead of just the one like quadratics do. All right, so with a cubic function, we don't have a single maximum or minimum, so we call it a relative maximum and a relative minimum, or you might see them called extremas. And the reason that it's relative and not the actual maximum, you can see if we are here, the graph goes higher than that, and it keeps going forever. So this isn't the true max of the graph, but it is a relative maximum, because that is where we have a change in direction. All right, so we are going to put that point there, and it's a little off, but it's close. I just want you to get as close as you can or make the best estimate. So we can see here, looks like our graph is going by ones, and we're at an x value of -2 and a y value of 1, 2, 3, 4. So our relative maximum is going to be -2, +4. And again, you can see it's a little off, but I just want you to get as close as you can. We're just making estimations. I just want you to see the graph and know what these parts of the graph are called. The relative minimum, so that's going to be where our graph curves, where it goes from down to up. So we always read graphs left to right. So our maximum is going to go up and then down, and then our minimums are going to go down and then up. So our relative minimum looks like we have a x value of about 1. It's not quite 1. This one I might feel a little weird about saying 1, so we might go with our estimation. And it goes down past -5, -6, -7, past -8, and it's just a little below that. So for this one, I think I'm going to estimate, just because I can tell it's even further off from the grid line than the first one. If you said +1, -8, I would be cool with that because I know you're in the general location. So I'm going to say it's probably about 0.9, and it goes down to about -8.1. Again, if you said 1, -8, I'm cool with that because I know you're in the general location and I know you have the correct point or the correct spot on the graph. X-intercepts. Cubic equations can have 1 to 3 x-intercepts. So we want to make sure and list them all. We can list them as x equals those values or as ordered pairs. I prefer ordered pairs, but I'll do both for you. So we cross here at -3, we cross at -1, and we cross at +2. So -3, -1, +2. Now I would prefer them to be written in this form. But if you write x equals, that's fine with me. Cubic functions still only have one y-intercept. And so we look at our y-axis, and we can see that it crosses the y-axis at -6. So again, you can write y equals -6, but I would prefer as an ordered pair because we're talking about a point on a graph, not a line. Now remember that the domain represents the x values, so where this graph exists along the x values. So this graph's going to continue to get wide forever and ever, and it's going to hit every x value on its way there. And on the right side of the graph, it's going to continue to get wider and wider. So it's going to hit every x value as it continues to get wider on the right side. And in between, it's hitting every x value. There's no break in our graph. So our domain is all real numbers. Or you can add in those math symbols I'm going to do it right here so it doesn't make my table any bigger. So you should be able to see this now. I'm going to click Insert, Symbols, Equation, and naturally it's going to mess up my tables. Okay, we're not going to do that, but we'll go through it one more time. And then that's where the infinity sign is. And if you don't see it there, you can click the drop-down menu and it has even more math symbols for you. But I'm going to not do that because it's going to mess up my table. The range, so the range of the y values. So this graph is going to continue to go down forever and hit every y value on its way. This graph is going to continue to go up and hit every y value on its way. So our range is also all real numbers. And again, you could do the negative infinity to infinity. End behavior. We're going to talk about what this graph is doing on the left side of the graph and what this graph is doing on the right side of the graph. So on the left side of the graph, it's going down, and on the right side, it's going up. So when our x values are getting smaller, our y values are also getting smaller. And when our x values are getting bigger, our y values are also getting bigger. So we can say when x goes negative, y also goes negative. Okay, this isn't quite the correct way, but for time, space, and the ability to type stuff, we're going to go. Okay, so this isn't greater than, this is like an arrow. So normally when we're writing it on paper, we would actually draw an arrow. Oh, and naturally it's like super big. So we would draw an arrow like that. As x gets negative, y gets negative. Again, this isn't quite 100% how you would see it normally written, but that's okay. And as our x values get big, so as our x values approach positive numbers, our y values also approach positive numbers. Okay, so this is just kind of like a basic, quick way to write it without having to do a bunch of formatting and stuff. If you want to put the arrows in, cool, do it. But you don't have to. All right, let's look at another one. As you can see, like my tables are messed up because I've written a little bit extra in the boxes, but that's okay. All right, so let's look at this new cubic function. We have a relative max, so we want to look for the little hilltop. And again, we're going to make our best estimation. So our x value looks like it's between 6 and 7. It might be a little bit closer to 7. So I might do like 6.6. And our y value, 15, 16, it's about halfway from 16 to 17, so 16.5. Sounds good? In the general area? Yeah. Our relative minimum, we're looking for the valley. So our x value is going to be about negative 1.5, right? And our y value, we're going to go down, and it's like right on negative 10, so that's awesome. Our x-intercepts, looks like we cross at negative 4. We cross at positive 2. And we cross at positive 10. Our y value, so we're looking at our y-intercept, we're going to look at the y-axis, and it looks like we crossed right at -8. And here's a little side note hint. On a on a cubic function, your domain and your range are always all real numbers. I'll see if it lets me do the math stuff, just so you can see it. Negative infinity to infinity and beyond. Okay, so that's how we would write it in interval notation. All right, now we talk about our end behavior. So on the left side of our graph, as our x values get smaller and smaller, our y values go positive. They get bigger. So as the x values approach negative numbers, our y values approach positive numbers. And on the right side of our graph, as our x values get bigger, so as our x values approach positive numbers, our y values are getting smaller. So as the x approaches positive numbers, our y values approach negative numbers. And what you're really supposed to do is you're supposed to put infinity in there. So if you want to do that to make it look better, you certainly can. You can even go and Control C, Control V, Control V, and Control V. So it's as x approaches negative infinity, y approaches positive infinity. But if you leave off the infinity sign, that's okay. All right, so I'm going to delete that so we can maybe get our tables back together a little bit. Let's see if I can get that. Oh, okay, the bottom. All right, there we go. All right, that is characteristics of cubic functions. Happy mathing.